This part of the topic deals with the application of the normal and historical VAR model to cash flow portfolios. So here we are in the lecture notes. Now, remember when you did the capital asset pricing model? You used regression. You didn't have to solve a quadratic equation, so your risk factor mapping technique was statistical, not doing some algebra. And your risk factor sensitivity is called an equity beta. In other words, with a simple risk factor model that you can get, that's a capital asset pricing model, you do a regression of the stock returns on the broad market index returns, and you find the fitted model that the return on the stock is alpha plus beta times the return on the broad market index. And beta is the coefficient of the change in that risk factor. And it's called, more generally, a risk factor sensitivity. But here we've got a completely different type of mapping, but we've still got risk factors and risk factor sensitivities. So we've got risk factors, which are interest rates of different, we've got a lot of risk factors, not just one, we've got a whole curve of risk factors at chosen vertices along a yield curve. And the risk factor sensitivities are going to be the change in the present value of the cash flow at each of these points along the yield curve. And it's the change in the present value when interest rates increase by 1 basis point. Later on, we can see real interest rate increases, or they might decrease. They might go down 1 basis point or 3 basis points. They might go up 4 basis points. But the PVO1 is the sort of multiple. So you can multiply the PVO1 by -5 basis points, and that will give you the total change in the portfolio value. But so that's the sensitivity to, just like the beta is the sensitivity to 1% increase in the stock market index. The PVO1 is the sensitivity to 1 basis point increase in the interest rate. So we call it PVO1, or present value of basis point, PVBP. I prefer PVO1. How do we calculate it? Well, if you've got a cash flow not in present value terms now, CI as maturity TI, spot interest rate RI. Okay, as before. And the present value of a basis point move, that's PVO1, is the sensitivity of that cash flow to a 1 basis point increase in RI, which is the expression on the right-hand side of this equation. So if we took it into two parts, you'd be dividing CI times all into 1 plus RI plus 1 basis point to the power TI. And then from that, you take the original present value, which is CI divided by 1 plus RI without the additional basis point to the power TI. For example, what's the present value of a cash flow of $5 million in 2 years' time when the 2-year interest rate is 4%? And so we take 5 million here and we calculate this. I've done a bit of rounding here and I get -890. So you've got a positive cash flow, 5 million, and a negative PVO1. If this were a negative cash flow, we'd have a positive PVO1. Let's have a look at this in the spreadsheet. Here, so we've got 2 years' time, interest rate 4%, cash flow amount 5, and we can find the present value in the usual way, just multiplying 5 by the discount, which is 1 over 1 plus B3 to the power B2, or we could have easily said 1 plus B3 to the power minus B2, same thing. And our PVO1 is actually, without the rounding, it's 889, not 890, because you've got some pretty big figures here, and I didn't calculate them to complete accuracy on the slide. So let's go back here now. So for one cash flow, PVO1 is the change in the present value at vertex TI when RI increases. So we're going to put it PVO1I for the vertex TI. And for a mapped cash flow portfolio to vertices T1, T2 up to Tn, you've got PVO1, PVO12 up to PVO1n, and we can collect them together in a vector. All vectors are column vectors, but I've just put a little transpose here so that I can just write it on a row. So we've got a whole vector, not just one beta, we've got a vector of cash flow sensitivities here. And now our factor model is what's shown in red here. It represents the change in the value of the cash flow portfolio, assuming that the P is held constant. Just in the same way as beta is the constant, and you can have different returns on the broad market index and see what the systematic part of the return is on the stock. We assume that P is constant, so the change in the present value of the cash flow, which is delta PT here, is going to be the sum of the changes in the present values. And now the PVO1 is the per 1 basis point increase, but now we multiply it by whatever the changes in interest rates were on that day. So we multiply it by R1, delta R1t up to delta RNT, and we can express that in matrix form here, where these change day by day. These are the vector of basis point changes in interest rates at time t. So let's have a look on our Excel spreadsheet now. So here in the spot rates. So, well, here, let me go to, this is going a bit further forward. This is for the next video, which is our case study. And I've only got data up to the 30th of September 2024, because that's when we're going to measure the VAR of this portfolio. And for the basis point changes, you can see that this is the change from here to here. So that is, let me blow it up a bit so you can see. So this is actually 4.09330,333. It's a very, very accurate measurement of these interest rates. Similarly here, every little bit matters, and you've got very large sums. And taking 4.16, whatever it is, from 4.99, whatever it rounded up to 4.10, gives me this number here, which is 6.18. It looks like 6 here, but it's not, because those are very rounded. And then this is our vector. So 6.18 is delta R1, this is delta R2, delta R3, delta R4 on 30th of September. But then on the 27th of September, the day before, this is the vector of the delta R's. Okay. Now we can look at the normal bar for cash flows. And we're going to now, because we've got a vector representation here, P prime RT, when we take the variance of this vector product, we get a quadratic form. It's because we can't write out the formula in summation form. I mean, it was easy for the cash flow mapping because we just had two things to deal with, that we could use that variance of AX plus BY formula, and it was easy. But here we've got a very large dimension, and so we're going to have to use matrices. And in the Excel spreadsheet for the var for a gilts portfolio, the next thing I'm going to use mmult a lot. So if you're not familiar with the form of this, before we had on topic 3 part 6, and it was on slide 58, we had W prime VW, where W were the weights and V was the covariance matrix. So this is very similar here. We've got P prime VP, where V is the covariance matrix, V delta R in particular. That's the covariance matrix. We keep P constant, that represents our portfolio on the 30th of September. That's the day when we measure VAR. And then we can use historical data in the entire spreadsheet with the covar command. And we find this covariance matrix. I'll go through that in detail, I think, when I go through the whole next section. Now, we're using daily data in that example, but we could have used weekly data. We could have used monthly data even. And the holding period for the VAR that you're going to get will depend on the frequency of the data. I'll say that one more time. The holding period of the VAR that you get depends on the frequency of the data. So we get daily VAR if we use daily data, and we get weekly VAR if we use weekly data. But whatever the frequency we get, we can always scale it with the square root of time rule in the usual way. So to summarize, suppose our data are daily. For example, they're daily changes. We take variances of our factor model, which gives us this equation in red here. V delta R is the covariance matrix of daily changes in interest rates. And then using zero mean in the normal VAR formula, we have, using the square root of time rule, because it's daily, we would scale up with the square root of H, and we need to multiply by the volatility. So I've also put the variance underneath that square root. And then we take the minus the quantile at 1%, if it's a 1% VAR, or in other words, we take the 99% quantile. And for the historical VAR, we just use this risk factor mapping directly. So we compute a whole column, one more column, from the row by row by row by row data on the basis point changes, delta RT, keeping P constant every time, and then calculating this sum product I'm going to use for this. So it's the sum product of a P vector with an R vector. So this gives a single column which we apply the percentile function to, and then we multiply it by -1, and that'll give us the 1-day VAR, assuming these changes, delta RT, are daily changes. It'll give us the 5-day VAR if those changes are weekly, and so forth. And then we just scale it using the square root of time rule. So there we are. Nice short video for this one, and only one more to go.